Thank you for joining me today, mathematicians, as we look at limits graphically. So, recall that a limit is what happens to the y values as the x values get close to some point. And so what we're doing now is we're just trying to find what happens graphically. So the idea is if I look at this function and I want to say find the limit as x goes to 2 from the left of f of x. What this means is that I want to pick a point where x is equal to 2. I'm going to pick an x value smaller than 2. So, and I don't want to go too big smaller because then I have to follow this whole thing. So I'm going to pick a little bit smaller. So let's start at, say, x equals 1. If I start at x equals 1, what happens is I get y equals 1.5. And so what I want to do is I want to let my x values get closer to 2. So I'm going to move in this direction, going off this way. Now, as I move in that direction, I want my other finger to follow the graph, and so now as I move, my finger is getting closer and closer to x equals 2, and now my fingers trace the graph along, and so what we notice is that we end up right here. And so what I want to ask is, what is the corresponding y value that I ended up with? Notice in this case that the y value I ended up with, if I trace this over, is going to be approximately 1. Since it's a graph, we don't know exactly, but we can find a good approximation just by looking at what it looks like. And so what I would say here is that as I followed my graph with x values slightly less than 2, I'm moving from the left to the right, I end up with my y values at approximately 1. So I would say that the limit as x goes to 2 from the left of f of x is just equal to 1. Now, if I do the same thing from the right, that is, I pick x values slightly larger than 2, and I follow them back to 2, then what I end up getting is that we can see that here's x equals 3, let's say, and here we would say y equals approximately 1/2. And so now I'm going to move my fingers back in this direction as they move in the x direction closer and closer to 2. And now if I let my top finger follow the graph, I get closer and closer to, well, at this point, notice that I am getting closer and closer to the same point I did last time. That is, I'm getting closer and closer to the point y equals 1. And so what we would say here again is that the limit as x goes to 2 from the right, so that is starting from the right and moving left to the point 2, we get that our limit is just 1. Now, because we got that the limit from the left was equal to 1 and the limit from the right was equal to 1, what we would say is that in either direction, our limit is going to be 1. Because in either direction the limit's going to be 1, what we're going to say is just that the limit as x goes to 2 of f of x is just equals 1. That is, the limit as x gets close to 2, regardless of direction of the function, is indeed going to be 1 because my y values approach 1. Now, additionally, what I could say is that if I want to find f of 2, well, the function value at 2 is I would plug 2 in, and I would follow that up. Notice that's basically the same point I've been finding both of these times, and so in this case I would get f of 2 is also equal to 1. Now in this case, this is going to happen actually quite a bit with functions, is that the limit from the left is equal to the limit from the right, therefore the two-sided limit exists and is equal to the same number. Furthermore, the function value is the same number as the limit value, and so when that happens we call this a continuous function. And continuous would mean that as I get close to 2 from the x value, or I get close to c in general in the x value, my y values are approaching some point. The function is equal to that point, and then I continue on afterwards moving away from that, so then I'm able to basically trace this without having to lift my finger. Now I've said that we have this nice property that we can trace right through the point, and we have these continuous functions at most of the points. But we're not always going to have continuous functions, so we still need to talk about limits when things that are more interesting happen. And so a lot of times we'll focus on the points that aren't like everything else so that we can get interesting examples. And so in that way, what I want to do is I want to start by looking at the limit as x goes to 0 from the left of f of x, because I want to determine what's happening going at x equals 0. Now if I start at x equals 0 and I move to the left, that means numbers slightly less than 0. We'll say, let's pick 1, negative 1 rather. If if I plug that in, it looks like my function value is approximately -1/8, -1/4, somewhere in there. But the idea is that, again, I'm going to trace the graph as my x values get closer and closer to 0, and what I want to know is what are my y values getting closer and closer to 2. And so as I trace this closer and closer to 0, I follow in, and notice that what I end up at is this point right here. So, therefore, I would say that as my x values approach 0 from the left, my y values are indeed approaching 0. So the limit as x goes to 0 from the left of f of x is just going to be 0. If I go through the same process again, this time from the right, I would find that the limit as x goes to 0 from the right of f of x, well, I would start to the right, so let's say about 0.5. At 0.5, my y value is 1.5. So now as I move in closer to x equals 0, we'll notice that my y values are getting smaller, and then eventually at this point, my y values approach this point right here, and that point right there would be the value y equals 1. That means that as I approached x equals 0 from the right, that as my y values came in, they got closer and closer to 1. Therefore, the limit as x goes to 0 from the right is equal to 1. Now, last time we had that these were both the same, so we said the two-sided limit was equal to the number. But in this case, we get from the left, we're getting close to 0. From the right, we're getting close to 1. So now if we kind of take a bigger picture view of this and say, well, what happens as x gets close to 0? Well, I don't know what happens. That is, some of the values are getting close to 0, some of the values are getting close to 1. Because these are going to two different places, I don't know what to expect if I just pick an arbitrary point close to 0, because that could be smaller or it could be bigger. So in this way, I would say that my limit as x goes to 0 of f of x is going to be does not exist. Or rather, my limit does not exist because I don't approach a single number. If I pick x values close to 0, I don't always get out the same y value, so my line does not exist. Now, the next thing we said is, well, what would the function value be? And if I get rid of the yellow I drew in here, remember this dot was filled in, this dot was not filled in when I drew this at the graph. So if I actually wanted to find f of 0, that would just be the point that is filled in. So that would be the y value 1. So here I could say f of 0 is equal to 1. So graphically we were able to find the limit from the left and the limit from the right and say that the two-sided limit did not exist. We were also able to find the function values, so my function is defined here, but it would not be a continuous function because I couldn't trace this without lifting my finger. Notice that if I trace this, I get to here. There's no way to get up to here without lifting my finger, or if I don't, I'm tracing through points that aren't on the function. So that's not allowed either, so I can't trace this without leaving the blue line and get up to here without lifting my finger. So that's what we mean by discontinuous. Thank you for joining me today, mathematicians. I hope you enjoyed this, and I hope you learned something along the way. If you did, make sure to like the video and to subscribe to the channel down here. This will help make sure that other people get to find this video so that they can also get help on calculus.